And we bridged from those rules of exponents into basic scientific notation. So I want to very quickly review the basic scientific notation and conversions, and then take a, expand on that and then leap into the next type of numbers that all this applies to. So if we have $490 million, and I want to convert that into scientific notation, what is it going to become? Perfect. 4.9 times 10 to the 8th. The 4 is our first non-zero digit, so we put our decimal point after that. And the 10 to the 8th, this is a large number, so it's going to be a positive power of 10 for our place value. This would be 0, 1, 2, 3, 4, 5, 6, 7, 8. That's in the 10 to the 8th place value. The shortcut, decimal point starts here. We had to move 1, 2, 3, 4, 5, 6, 7, 8 spots to get it to the point after the 4. Remember, what that really stands for is this is the 10 to the 0 place value, 10 to the 1, 10 to the 2 on up, and that 4 is in the 10 to the 8th, or the 100 millions place value. So 0.000032 becomes what in scientific notation? Perfect. 3.2 times 10 to the negative fifth. The 3 is our first non-zero digit, so we move our decimal point to be after the 3. And that 3 is in the 10 to the negative fifth place value. Again, the shortcut, this is a very small number. It's smaller than 1, so our place value has a negative power of 10. Decimal had to move 1, 2, 3, 4, 5 spots, so that is 10 to the negative fifth. So when we look at our scientific notation here, 4.2 times 10 to the 13th, and I compare it to our whole numbers. When we were working with whole numbers, like 426 plus 352, we could only add straight down the columns because we had to add, you could only combine ones with ones, tens with tens, hundreds with hundreds. We could only combine digits that have the same place value. What part of the scientific notation implies a place value? If you remember, yeah, it was 10 to the 0, 10 to the 1, 10 to the second, 10 to the third. Those were our place values. So what part of this up here implies a place value? Yeah, 10 to the 13th is a place value. So this is an extremely large number. What's that saying is that 4 is in the 10 to the 13th place value. So this is an extremely large number. So when we're looking at scientific notation, to go back to the terminology we used that first week, the 4.2 is our count. The 10 to the 13th is our place value, or the name. So to review, when we add or subtract numbers, first, we need the same name. Now in any operation, we're going to combine the counts. When we add or subtract, what do we do with the names? We keep the same name. So when we're looking at adding or subtracting numbers in scientific notation, first of all, we need the same name implies that the two numbers have to have the same power of 10. 4.3 times 10 to the 9th plus 3.1 times 10 to the 9th. Those numbers have the same name. They're both 10 to the 9th. Next, we're going to combine the counts. So that means we add 4.3 and 3.1 to get 7.4. Good. Then we keep the same name, so it's times 10 to the 9th. So our rules for adding numbers in scientific notation are the exact same rules for adding numbers in any other form. So we might have 7.5 times 10 to the 12th plus 4.2 times 10 to the 12th. Do they have the same name? Yeah, so we can go ahead and add. So we combine the counts. What do we get?
11.7 times 10 to the 12.
Perfect. Combining the count, 7.5 plus 4.2 is 11.7. Then we keep the same name, so times 10 to the 12th. When we look at that, there's an issue there. That's not proper scientific notation. There are 2 digits in front of the decimal point. So we're going to have to adjust it. We adjust it to make it so that there's only 1 digit in front of the decimal point. So that decimal point moved 1 spot. Well, every spot the decimal point moves is a power of 10. It's a change of 1 in that power. So did the number get larger or smaller? It went from 11.7 to 1.17. It got smaller. So to make up for it, the power has to get larger by 1. So that becomes now 10 to the 13th. Very good. So I'm going to have you try 8.6 times 10 to the negative 9th plus 7.9 times 10 to the negative 9th. I'll give you about 20 seconds or so to see what you come up with there. So we combine the counts. What is 8.6 plus 7.9? 16.5. Very good. Times? Yep, 10 to the negative 9th. What has to be adjusted there? Or what is it going to become? So this is the part to be careful with. Times 10 to the negative 8th. Good. The number got smaller. It went from 16 down to 1.6. The power has to get larger. Negative 9 plus 1 is negative 8. If we have different powers of 10, let's say I have 9.63 times 10 to the 13th plus 7.4 times 10 to the 12th. we can't add those the way they're written. We have to adjust them. We have to rename them so that they have the same name, just like we did with fractions. Normally, for scientific notation, we go to the larger power of 10. So 10 to the 13th is the larger one, so that one's going to stay the same. 10 to the 12th is going to become 10 to the 13th. Now when we change the power, we have to adjust the number. The power got larger by 1, so what does the number have to become? Perfect, 0.74. Power got larger by 1, the number has to get smaller by 1 decimal place. Now we go ahead and add 9.63 plus 0.74 is? There you go, 10.37, perfect. Times 10 to the 13th. And we're going to have to adjust that to make it perfect. 1.037 times 10 to the 14th. The number got smaller by 1 place value, so our power of 10 gets larger by 1. Subtracting works the same way. We have to have the same power of 10. 5.3 times 10 to the negative 11th minus 2.5 times 10 to the negative 11th. We combine the counts. What's 5.3 minus 2.5? 2.8. Good. Times 10 to the negative 11th. We may have 6.13 times 10 to the 14th minus 5.81 times 10 to the 14th. When we go to subtract, we combine the counts. 6.13 minus 5.81 becomes 0.32 times 10 to the 14th. Now that has to be adjusted. Now there's no digits in front of the decimal point, only a 0. Remember, it has to be a non-zero digit. So we adjust that to make it what? 3.2. Now the number got larger, so the power gets smaller. So it becomes 10 to the 13th. Good. So we have 5.27 times 10 to the negative 9th minus 4.52 times 10 to the negative 9th. In your notes, I'm going to give you about 20 seconds to work that one out. So 5.27 minus 4.52 is 0.75 times 10 to the negative ninth. Perfect. We adjust that to become what? 7.5 times 10 to the negative 10. Good. Number got larger, went from 0.75 to 7.5. Power gets smaller. So negative 9 minus 1 is negative 10. Perfect. Let's multiply. Start like 4.2 times 10 to the ninth times. Now remember, we multiply or divide. Do we need the same name? No, we do not need the same name. So this can be times 1.5 times 10 to the 12th if I want it to be. So then we're going to combine the counts, just like we always do for any calculation. But then when we multiply or divide, we also combine the names. So up here, we're going to multiply the 4.2 times the 1.5, which gives us 6.3, but we also combine the names. 10 to the ninth times 10 to the 12th is 10 to the 21. Remember, when we multiply exponents, we add the powers. So we may have 4.3 times 10 to the negative 18th times 5.6 times 10 to the 7th. We're going to multiply the counts. What is 4.3 times 5.6? Perfect, 24.08. Good. Times 10 to the? Perfect. 10 to the negative 18th times 10 to the 7th is 10 to the negative 11th. Now that has to be adjusted because we now have two digits in front of our decimal point. What's it going to become? 2.408. Good. Times 10 to the negative 10. Good. The number got smaller. Went from 24 to 2.4. Power gets larger. So negative 11 plus 1 is negative 10. Division. $5.76 times 10 to the 12th divided by 1.2 times 10 to the 5th. We combine the counts. What is 5.76 divided by 1.2? 4.8. Very good. Times 10 to the 7th. Very good. 10 to the 12th divided by 10 to the 5th. When we divide exponents, we subtract powers. So 12 minus 5 is 7. We may have 6.76 times 10 to the negative 11th divided by 5.2 times 10 to the, what do I want to put in here? Well, let's go 10 to the 7th. What the heck? So we have 6.76 divided by 5.2 gives us 1.3 times 10 to the perfect, negative 18. We subtract the powers. Negative 11 minus 7 is negative 18. Might have 3.24 times 10 to the negative fifth divided by 3.6 times 10 to the negative 13. I'll give you a minute in your notes to try that one. So we divide. 3.24 divided by 3.6 gives us 0.9 times 10 to the eighth. Good. 10 to the negative fifth divided by 10 to the negative third. We subtract negative 5 minus negative 13 is negative 5 plus 13, or 8. Now that has to be adjusted. What is it going to become?
9 times 10 to the 7.
Perfect. 9 or 9.0, depending on how you want to list it, times 10 to the 7th. Number had to get bigger, so the power got smaller. If I'm going to square a number in scientific notation, just like when we dealt with algebraic numbers, some basic operations with algebraic numbers, if we had 5x to the third and we squared it, we squared the 5. What was 5 squared? 25. Then we x to the third to the power of 2 is x to the 6. Remember, we take a power, we multiply powers. The process with our scientific notation looks very similar. It's the same process. 2.4 squared is 5.76. Good. Times 10 to the power of 22. Good. 10 to the 11th squared, we do 11 times 2 is 22. We might have 6.2 times 10 to the negative 8th to the power of 4. So we have to do 6.2 to the power of 4. 1477.63 will go. We're going to round it at that point. Times 10 to what power? Negative 32. Good. Now this time we have to adjust the decimal point. How many spots? 3 spots. Remember, every movement of the decimal point, we're going to round that to 1.478 about. Every movement of the decimal point is a power of 10. So the power of 10 has to change by 3. Did the number get bigger or smaller? It got smaller, right? 1400 down to 1. So the power gets larger. So negative 32 plus 3 is 10 to the negative 29. Any questions there? That's where my 24 went. So what if we have a square root? Well, same as we would do with algebraic numbers, we take the square root of the number. What is the square root of 6.76? 2.6. Good. It becomes 10 to the power of? Perfect. 7. When we squared that number, up here when we squared it, we multiplied the power by 2. Well, square rooting is the opposite of squaring, so it makes sense that we would divide that power by 2. So the square root of 10 to the 14th is 10 to the 7th. When we look at exponents more closely in a couple of weeks, one of the things we go over is the fact that a square root, the square root of x, is equivalent to x to the power of 1/2. So that makes even more sense. 10 to the 14th to the power of 1/2, 14 times 1/2 is 7. What if we have a bigger root? Like the third root of 1.728 times 10 to the negative 21. What's the third root of 1.728? Do you guys remember how to do that? Some of your calculators have a third root key on them. Others will have to use the x root or n root key. I put in 3 first. On my calculator, I have to go through the math menu to get to the x root. And then I type in the 1.728. Should give me 1.2. And it does. Times 10 to the perfect. When I did a square root, I divided by 2 on my power. When I did a cubed root, I divided the power by 3. So the cubed root of 10 to the negative 21 is 10 to the negative 7. Now there is a very close tie between the scientific notation and our algebraic numbers, often referred to as polynomials. Let me try that again. There, I can read my own writing. As we saw in last class with our scientific notation, our place values are 10 to the 0, 10 to the 1, 10 squared, 10 to the third, 10 to the fourth, and so on. Now we alter these last couple. 10 to the 1 is just 10, so we don't usually put the power of 1 on it. 10 to the 0 is just 1, so we don't even write, 1 doesn't alter anything's value, so we usually just leave that as well. So when we have a number in long form, like 427, we can write that as 4 times 10 squared, because that 4 is in the 10 squared place, plus 2 times 10, because it's in the 10 to the 1 or just the tens place, plus we could do 7 times 1, but since 1 doesn't change things, we typically just write it as 7. From that representation, when we look at an algebraic number or polynomial, 2x squared plus 5x plus 9, we can see the similarities there. It's just down here, our place values now are x squared, x, and x to the 0, or 1s, where up here it's 10 squared, 10, and 10 to the 0, which is still 1s. And because of that, our algebraic numbers or polynomials work exactly like any other numbers we've worked with. Scientific notation, our whole numbers, and so on. Now, some of the things we have to look through is differences between our polynomials and our integers. In an integer, either every digit is positive or every digit is negative. If I have a negative 438, that is a negative 4 times 10 squared plus a negative 3 times 10 plus a negative 8 ones. In a polynomial, however, each digit is free to be positive or negative on its own. So I can have 3x squared, a negative 7x, and a positive 5. The other big difference that we should point out is that in our base 10 numbers, we can't have any digit that's bigger than 9. Once that digit becomes a 10, it goes over to the next place value. We carry. In algebraic numbers, there is no carrying. We could have 5x squared plus 19x. Doesn't matter that it's more than 10. Minus 13. Again, it can be negative. Each digit can be negative or positive, and we don't have to worry about carrying. So other things that we can now have to be able to do with these polynomials. Well, I want to name some names of the polynomials, some vocabulary. We've seen the polynomials really aren't any different from whole numbers, but most textbooks do treat them quite a bit different. And because of that, a lot of textbooks throw out quite a bit of vocabulary with our polynomials. So let's take a look at just a simple polynomial like we had up above. 8x squared minus 12x plus 3. First thing is the number of terms. A term is just a digit. If I had a whole number, 248, how many digits does that have? 3. This number over here, how many digits does it have? 3, right? So that is a what's that? It's still one digit. It's 2 digits of a number, but it's still only one digit. It's one place value. That's the x place value. So this is 3 terms. Now there are special names for 3 terms that we'll talk about in just a second. Other vocabulary we want to talk about. Coefficients. In my integers up here, the coefficient is the number that's multiplying the place value. Of course, this is a negative 4, a negative 3, and negative 8 are the coefficients. So down here, my coefficients are 8. I'm going to list them over here. My coefficients are 8. What's my next coefficient in that next term? Careful. Negative 12. There we go. And then the last coefficient is 3. Even though there's no variable there, it is still a coefficient. Because remember, that is technically x to the 0, right? So it's still a coefficient. Next thing they define is degree. Each term has a degree. Now in the whole numbers and integers, we could define it as well. It makes a lot more sense in the polynomials than it does in our whole numbers. The degree is a power, or the power of the exponent. So each term has a degree. This term has a degree of what? 2, because the power on our exponent is 2. It's x squared. This term has a degree of 1. That's technically x to the 1. This term has a degree of 0, because that's technically x to the 0. The whole polynomial has a degree equal to the degree of the largest term. So this is said to have a degree as the whole polynomial of 2, because that is the degree of the largest term, largest degree. Just like up here for our whole numbers, if I can get up here, 427, we would say that that is in the hundreds, because that is the largest, the place value of the largest digits. You know, if it was 2,854, we would say that that number is in the thousands. Basically, we're saying it has a degree into the thousands place, or the 10 to the 4th place. So, our polynomials can be named by the number of terms. A polynomial with one term is referred to as a monomial. An example of this might just be 7x. That's a monomial. 19x to the 5th. That's a monomial. 3x to the 8th, y to the 4th. That's a monomial. One term. Notice, to be a term, it has to have both a count and a name. It can have multiple names, however. The 3x to the 8th, y to the 4th is only one term because there's only one count there. It has a count of 3, and there are 2 names, x to the 8th, y to the 4th. It actually combines. It's kind of like for people hyphenating the last name. I've got a friend who is Johnson Evavold. Well, same thing. This is x to the 8th, y to the 4th is considered a single name now. If there are 2 terms, it is called a perfect binomial. So examples of that might look like 5x minus 2 could be a binomial. 9x to the 5th, y to the 8th, plus 11x to the 3rd, y to the 11th. That's a binomial. Each of them has 2 complete terms. 2 sets of account and its names. Account and its names. If a polynomial has 3 terms, so I put my R in there, it is called a trinomial. Good. Tri meaning 3, of course. So our trinomials, most common trinomials look something like 2x squared minus 9x plus 5. But it could be any combination of 3 algebraic digits. Could be 7x squared y to the 5th plus 2z minus 8. That's also a trinomial. There's 3 separate digits, 3 counts along with its names. When we get larger or more than 3, it's a little simpler. A polynomial with 4 terms in it, 4 digits in it, is simply referred to as a 4-term polynomial. And so on. 5 digits, 5 terms would be 5-term polynomial, and working its way up from there. Now this polynomial is obviously not in order. It's not proper. It would be considered poor grammar. We'll talk about that in a second. But how many terms does it have? 4 terms. Very good. What are its coefficients?
28, 32, 7, 4.
Perfect. 28, negative 32, 7, and negative 4. Very good. What is the degree of each term? This first term has a degree of 5. This term has a degree of 1. This term has a degree of 8. And this last term has a degree of 0. So what is the degree of the polynomial? The largest of any of the degrees of the terms is 8. So this is a degree of 8 for that polynomial. The degree of the polynomial, if you moved on into getting solutions for polynomial equations, the degree of the polynomial actually tells us how many solutions that polynomial equation should have. So anyway, moving on from here, we can evaluate a polynomial. So if we're asked to evaluate the polynomial 3x to the third plus 7x squared minus 9x plus 13 for x equals 2. What are we going to do? Yeah, put 2 in wherever there's an x. So this, instead of 3 times 2, or 3 times x to the third, becomes 3 times 2 to the third. So 7 times x squared, it's 7 times 2 squared. Instead of negative 9 times x, it's negative 9 times 2. Of course, 13 doesn't change because there's no variable there. Now what? Yeah, we do our order of operations to solve, or to evaluate. Do our powers first. 2 to the third is, careful, 8. 2 times 2 times 2 is 8. There we go. 7 times 2 squared is 2 times 2 is 4. High energy today. So now we can go back. We've done all of our powers, exponents. Multiplication and division going left to right. What's 3 times 8? 24, good. 7 times 4. 28. 9 times 2? 18. Now again, I can treat that as minus a 9 times 2, so minus 18. Or I can treat it as a negative 9 times 2. That would be plus a negative 9 times 2. So it becomes plus a negative 18. They're the same thing. Of course, we still have plus 13 there. So now we can add and subtract left to right. 24 plus 28. 52. 52 minus 18. 34. And 34 plus 13 is 47. So that polynomial evaluates to be 47. Now, one thing you will notice, I wrote this polynomial in a very specific way. I had mentioned in this previous example up here that this polynomial would be considered improper or bad grammar. The reason for it is I just kind of randomly placed the terms in there, the digits in there. Whereas down here, in this example, you'll notice the degree, if you look at the degree of the terms, they fit a pattern. This has a degree of 3. This has a degree of 2, 1, and 0. They go from the largest degree to the smallest degree. That is what's referred to as descending order. So largest degree to smallest. And typically that is the way we want to express our polynomials. So up here, if I wanted to rewrite this in descending order, what term would come first? 7x to the 8th is the largest degree of any of the terms. What would be next? Plus 28x to the 5th. Good. That is the next largest. What's next? Negative 32x. That's the next. And finally, minus 4. That would be descending order. There is something called ascending order. And you might get asked to do it every now and then. It's just an exercise really in adjusting the symbols, because mathematically we tend to prefer things in descending order because that's what our place values of whole numbers are. Those are descending order. It starts out with the larger power of 10 and goes down to the smaller ones. Ascending order, if I have 3x to the 5th plus 17x squared minus 5x to the 4th plus 2. Ascending order goes from smallest degree to largest degree. So what would go first if I were to put this one in ascending order? 2. Good. What would be next?
17x squared.
Plus 17x squared. Good. And then?
Minus 4x to the 4th.
Minus the 5x to the 4th. Yeah, I know what you meant. And then?
Plus 3x to the 5th.
Plus 3x to the 5th. Very good. Now you'll notice in these last couple of polynomials that we put in ascending or descending order, not every power was there. There are some powers missing here. When we deal with whole numbers, every power, every degree is accounted for. We might have 504,209. If I were writing that out in expanded form, that would be 5 times 10 to the 5th. Do I need to put down that place? No, that's just a 0, right? We don't have to include it. Plus 4 times 10 to the 3rd. That's the 4. Plus 2 times 10 squared. I don't put anything in for that. That's just 0. And plus that 9 ones. Well, that's exactly what's happened here, is we've left out those place values that had zeros in them, basically, because our algebraic numbers are always written out in expanded form. But when I look at this, I have to fill in those missing place values, those missing powers of x. So I start out with the 7x to the 5th, but I have to slip in here a 0x to the 4th because there is no x to the 4th up here. I have a positive 5x to the 3rd, the positive 3x squared. Again, there is no x to the 1 or x up here, so I have to fill in 0x, and then the negative 8 ones. In a lot of our calculations that we do, we're going to need those missing digits in that polynomial. Other cases, we may need to reduce a polynomial, combine some digits. We might have 7x to the 4th minus 5x squared plus 2x minus 3x to the 4th plus 1. How many terms does this polynomial have? And be very careful. It is not 5. Why is it not 5 terms? There we go. The 7x to the 4th and negative 3x to the 4th can be combined to make 4x to the 4th. Good. Minus 5x squared plus 2x plus 1. So that is only a 4-term polynomial because 2 of the terms needed to be combined before it was in its simplest form. So from these, what we've learned here with our basics, our next step is going to be to start calculating with our polynomials. Just like with whole numbers, when we had 735 plus 252, when we wrote those out into long form, this was 7 times 10 squared, 700s, plus 3 times 10, 3 tens, plus 5 ones. This was 200s, or 2 times 10 squared, plus 5 tens, and 2 ones. We could only add the digits that had the same place value. 5 and 2 made 7 ones. 3 tens and 5 tens made 8 tens. 700s and 200s make 900s. So that was 987. Now, because we use the abbreviated version for most whole numbers and integers, we could do it with the abbreviated version. The difference when we start working with polynomials is our polynomials are always written out in that expanded form or long form. So if I have 5x squared, and of course they can have negative digits, minus 12x plus 3 plus 2x squared plus 6x minus 18. When I go to add those, now there are shortcuts that we've been taught. Most of us have actually been taught the shortcut just when we're adding here, just take out parentheses and combine the like terms, right? Sound familiar? But we can go ahead and add these just like we do with whole numbers. 5x squared minus 12x plus 3. We're going to line up the columns just like we did with our whole numbers. So the 2x squared goes under the 5x squared. The 6x goes under the negative 12x. The negative 18 ones goes under the positive 3 ones. And we are adding down our columns. What is 3 plus negative 18? Negative 15. Negative 12x plus 6x. Negative 6x. Perfect. 5x squared plus 2x squared. 7x squared. Just like dealing with our whole numbers. So I might have 13x to the third plus 9x plus 11, or minus 11, plus 7x squared minus 13x plus 2. When I write out this first number, what am I going to have to do? What's missing in that? There's no x squared, so I have to put in 0x squared. So then plus 9x and the negative 11 ones. This number then lines up. The 7x squared lines up with the 0x squared. Negative 13x lines up with the 9x. And the 2 ones goes with the negative 11 ones. And we are adding. So negative 11 plus 2 is negative 9. 9x plus negative 13x. Negative 4x, good. 0x squared and 7x squared. 7x squared, that's positive. And then, of course, 13x to the third. Now, we would have got the same result using our shortcut, just removing the parentheses and combining like terms. Nothing to combine with the 13x to the third, so that's going to stay the same. Nothing to combine with the 7x squared, that stays the same. You combine the 9x and negative 13x, give you the negative 4x. Negative 11 and 2 combine to give you the negative 19. So removing those parentheses and combining like terms is a shortcut. It does work. Feel free to use it because I know that's what most of you are taught. But this is the actual long process of adding polynomials. Subtraction. So I might have 5x squared plus 7x plus 12 minus 8x squared plus 3x plus 1. Again, I'm going to line up the columns. So I write it out, 5x squared plus 7x plus 12. 8x squared goes under the 5x squared. 3x goes under the 7x. The 1 goes under the 12. Now we are subtracting. 12 minus 1 is 11. 7x minus 3x, 4x. 5x squared minus 8x squared, negative 3x squared. Good. Subtraction gets a little trickier when we include the fact that each digit can be positive or negative on its own. We can have negative 3x squared plus 9x minus 5 minus 7x squared minus 13x plus 4. We'll still line this up just like we have any of the others. Remember that we are subtracting down each column. It's just a little trickier now. What's negative 5 minus 4? Negative 9. What's 9x minus a negative 13x? What's 9 minus a negative 13? Positive 22x. Negative 3x squared minus 7x squared? Negative 10x squared. Perfect. That can be a little trickier. Many of you were probably taught a shortcut. that when you're subtracting, you change the sign of every term in that second one. This becomes negative 7x. This will become, or 7x squared. This will become positive 13x. That'll become a negative 4 ones. Change that to addition, and you remove the parentheses. Does that look familiar? You change the sign of every term in the second one. And now it is 7x, or negative 3x squared and negative 7x squared make 10x squared. 9x and 13x make 22x. Negative 5 and negative 14 make negative 9. Well, all that's doing is doing what we did in each column. Negative 5 minus 4, you could change that to negative 5 plus a negative 4. 9 minus a negative 13, you change that to 9 plus 13. So all we did was we changed all the signs at once there. It's just a shortcut for doing the subtraction. Where this one becomes confusing to me, and the long version is more beneficial, for me at least, is when we have things like this. 2x squared minus 7x plus 11 minus 5x to the third plus 8x minus 5. So when I go to write this out, I have 2x squared minus 7x plus 11. But I have 5x to the third. Where does that have to go? It has to go out here, doesn't it? I have no x squared, so I got to put in 0x squared, 8x, and my minus 5. And I am still subtracting. To make this work, however, I have to put in a 0x to the third, because there wasn't one in that first polynomial. Now I can subtract. What is 8 minus a negative 5? Or sorry, 8. What's 11 minus a negative 5? 16. Negative 7x minus 8x. Negative 15x. 2x squared minus 0x squared. 2x squared. 0x to the third minus 5x to the third? Negative 5x to the third. Any questions on that? Okay. Well, our next step is to start talking about multiplying and dividing these polynomials. I want to simply review multiplying and dividing monomials first, and then we'll pick up on Monday with the polynomials. If I am multiplying 8 x to the fifth, y to the third, times 9 x to the second, y. Remember, just like any other number, I have to combine the counts. What is 8 times 9? 72, right? Perfect. Then we combine the names, and we can go each name separately. What is x to the fifth times x squared? X to the seventh, good. Y to the third times y? Y to the fourth, good. We think of that as y to the 1, so 3 plus 1 is 4. We might have 4x to the fifth, y to the eighth, times negative 7, x to the negative 7th power, y to the third. We're going to combine counts. What is 4 times negative 7? Negative 28. X to the fifth times x to the negative 7th. X to the negative 2, good. Y to the 8th times y to the third. Y to the 11th. Now, a little bit of review from yesterday. If we were asked to express this with only positive powers, what would we have to do? Perfect. X squared goes to the bottom to make it a positive. The negative 28 still stays on top because that's a number. It's a coefficient. We can't change the sign of a coefficient by moving it. We can only change the sign of a power within an exponent by moving it within the fraction. If we divided 32x to the 8th, y to the 5th, z to the 6th, divided by 8, x to the 4th, y, z to the 5th. We combine the counts. What's 32 divided by 8? 4. X to the 8th divided by x to the 4th? X to the 4th. Y to the 5th divided by y? Y to the 4th. Good. Remember, that's y to the 1, so 5 minus 1 is 4. And z to the 6th divided by z to the 5th? Just z. Remember, 6 minus 5 is 1, so z to the 1 or just z. We might have 40 x to the 5th, y squared, z to the 3rd, divided by negative 5, x squared, y to the 3rd, z to the, let's go z to the 5th. So we divide 40 divided by negative 5. Negative 8. How about for x? X to the 3rd. Good. 5 minus 2 is 3. How about y? Negative first. 2 minus 3 is negative 1. Z? Negative second. 3 minus 5 is negative 2. If I wanted to make that positive powers, what would it be? Y is z squared, right? So the negative 8 can't be changed. That's going to stay on top. Negative 8 x to the 3rd. The y to the negative 1 moves to the bottom and becomes y to the positive 1, or just y. The z negative 2 moves to the bottom, becomes z to the positive 2. Okay, we're down to less than a minute left, so I'll let you guys out of here. Remember, you should be working on homework 6B. Of course, homework 6A and B will be due on Monday. And quiz 6 is also due for Monday. Also remember, if you haven't received your test and email, please send me a message so that I can get it back to you. If you can't read, if you can't see the inking, if you can't see the score and which ones are marked wrong, try to open it on a WITC computer. Otherwise, let me know and I'll try to resave it as a PDF and send it to you. You can redo those problems again. Make sure you're doing those corrections. Okay, we'll take some time on Monday to answer any questions on the test. Feel free to remind me if I forget. You guys have a great weekend. Thank you.